Greetings, statistics scholars, and welcome to this video from section 6.2 of your text, dealing with the idea of using t-distributions to make inferences about population means. In this video, we are going to focus in on some technology skills to help you with the inferences from this section. First, let's discuss the idea of the t-distribution. On your screen here, you see a picture of a man named William Seeley Gossett. He was an employee of the Guinness Brewing Company around the turn of the 20th century. In the early 1900s, Gossett, an employee of Guinness Brewing Company, did pioneering work that has helped us to understand how sample means are distributed when there are small sample sizes. Gossett was interested in the variability of the yields of barley plants for his work at Guinness, and as he studied those, he found something interesting. What he found was that the statistics, the sample means, were distributed in a way that was shaped largely like the standard normal curve with a bell shape, but with one crucial difference. Gossett found that as the sample sizes grew smaller, the distribution became flatter and the tails of the distribution became thicker. We've introduced here a notion of something called degrees of freedom. You'll see in the picture DF. DF stands for the number of degrees of freedom for a t-distribution. Degrees of freedom are defined so that they're always one less than the sample size. So in the picture, the curve you see labeled with 13 DF refers to a situation where samples of size 14 were taken. If samples of size 6 are taken, then DF is 5, resulting in the other curve. Notice that both of these curves have more area in their tails than the standard normal distribution does. Gossett was an important pioneer, and his work to help us understand the distributions of the sample means now gives us some of the tools that we need to help make sounder inferences, whether we're making confidence intervals or whether we're doing hypothesis tests. So let's look at some technology skills then. One of the things that we often want to do is to create a confidence interval. Suppose that we're trying to create a confidence interval for a population mean. Suppose specifically that we're trying to make a 90% confidence interval for a population mean, and we've had 35 data points in our sample. We know, of course, that we're going to put our sample mean right in the center of the confidence interval, but how wide should the interval be? To determine that, not only do we need to figure out what the standard error of the mean is, but we also need to find out how many standard deviations we need to include in order to attain the level of confidence that we want. In order to find that value, which we refer to as a t-value or a t-star value, we can utilize our Statkey to help find this out. In Statkey, if we go to the theoretical distributions and find the t-distribution option, once we go there, we'll always be prompted to enter the number of degrees of freedom that we want. This will always be our first step to change the number of degrees of freedom to what is appropriate for the problem. In this case, there were 35 in the sample, and our definition of degrees of freedom says that they are one less than the sample size. So for our degrees of freedom here, we'll indicate that we want 34. Once we've entered that, Statkey will sketch a distribution for us. We would like to have a confidence interval here. And the fact that we want our confidence interval means that in our next step, we want to indicate that we would like to look at two tails, specifically because we would like to indicate the area between the two tails that we would like for that will be our confidence level. Once we've clicked on two tail, Statkey will set up a picture that usually has 95% of the area between the two tails. It's set up to default to a 95% confidence interval. If we would like a different level, suppose 90% as in here, we next could go to the center of the distribution and find the proportion right in the middle, and we can edit that proportion to be exactly the confidence level that we would like. If we want 90%, we'll edit that proportion to be 90%. If we're looking for 99%, we'll edit that proportion to be 99%. As soon as we do that, Statkey will redraw the distribution to put the requested proportion in the middle and the remainder of the area in the tails. And Statkey will then report to us our result. Our result here, by looking at the bottom, we can see the particular cutoff values that are necessary in order to achieve the level of confidence that we entered. These values at the bottom are what we refer to as our T values or our T star values. Those are the values that will be used when we're computing the margin of error from the sample, from the standard error of the sample means and from our T star value. So this is one important skill. If we're looking to find T star values to help construct a confidence interval, that is the process that we will follow. But another type of inference that we often want to do is to do a hypothesis test. And if we're doing hypothesis tests, deciding any hypothesis test means we need to know a p-value that we can compare to our level of significance. But how will we find p-values for hypothesis tests involving population means? Let's take a look at that now, and how we can use Statkey to help find areas underneath t-curves and thereby find p-values. We're going to suppose here specifically, for the purposes of example, that we're doing a left-tailed hypothesis test for a mean. And we're going to suppose that we have gotten a t-score of negative 1.75. Furthermore, we're going to assume here that there were 22 individuals in our sample. Well, you may recall from before, the moment that we go to look at the theoretical t-distribution in Statkey, we're always going to be prompted to indicate the number of degrees of freedom. Our first step is going to be to change the degrees of freedom here to 21, as there were 22 cases in our sample. Once we've entered the appropriate number of degrees of freedom, Statkey will draw the t-distribution, and then we have to decide in our second step, what kind of hypothesis test was this? Was it left-tailed? Was it right-tailed? Was it two-tailed? We'll choose the particular checkbox that is appropriate to our hypothesis test. Here I've clicked on left tail because we're doing a left-tailed test. Once we've done that, Statkey will traditionally draw the curve so that there is an area of 2.5% to the left of the given point. But what we would like to do is we would like specifically to know what the area is that corresponds to our t-score. So what we need to do is to change the cutoff value here. We'll go to the bottom of our screen and click where the cutoff value is, and we will adjust it to whatever our t-score was. If our t-score was negative 3.7, we'll type in negative 3.7. If our t-score was negative 0.72, we'll make it that. But in this case here, we're assuming that we had a t-score of negative 1.75. So that's the value that I've entered. As soon as I enter the cutoff value that corresponds to my t-score, we can count on Statkey to redraw the curve to shade in the area, in this case to the left, since this was a left-tailed test, and to report my result. This result that we see above the curve here is the area that was underneath the curve, in this case to the left of my cutoff value. That area underneath the curve would then be interpreted as the p-value for my hypothesis test. In this particular case, we have a p-value of 0.047. That's going to be significant at the 5% level and also the 10% level. So there you have it. We've looked at two key skills in this video: how to find t-star values that will help us compute the margin of error for confidence intervals, and how to find p-values, which are areas underneath the t-curve. I hope you found this video informative and useful as you go to work exercises and examples from your text.